Hello everyone, and thank you for the introduction. Today I'm going to present a technology we've been working on for the last 10 years or so to do petrophysical multimineral analysis using genetic optimization, not only to solve complex mineral composition in unconventional reservoirs, but also to do it faster. Our main goal is to introduce a new method to accelerate the path between well logs and results in unconventional reservoirs. First, we're going to revisit the fundamental difficulty when estimating mineralogy in unconventionals. Then, we will show the typical results derived from the standard approach for multimineral analysis and discuss the assumptions and limitations of this approach. We will see that one of the main limitations of the standard process is that it is very slow. And then, we will show an example of a problem that can be addressed if we overcome this limitation. Then we will introduce an approach for a faster genetic algorithm-based multimineral analysis, and we will see that the main advantage of this approach, speed, can bring new insights into the analysis, which allow the petrophysicists to generate solutions that are very difficult to obtain with the standard approach. Here's how rocks measurements and models relate to one another in the problem of multimineral analysis. First, we'll start with a rock that is composed of different minerals represented here by different colors. This particular rock, for instance, is made out of dark, light, and brown minerals. Then we run our logging tools along the well and obtain a set of well logs where each of them hopefully will respond differently to the different minerals present in the rock. So what do we do with these logs? Well, ideally, we would like to use them to recreate the original picture, but this is an impossible goal for a variety of reasons. So we settle for a less ambitious goal. We make different assumptions about how measurements, minerals, and fluids in the rock relate to one another, and based on these assumptions, we perform inverse modeling. The result is a model of the rock that is typically a fuzzy version of the reality. For instance, here, we did a pretty good job in estimating where the dark mineral is, but at the same time, we mixed up the light and the brown and ended up with the mineral that has more lighter colors than expected. Why is this important? Because if lighter colors were related to quartz minerals, for instance, we would end up with a rock that would look more brittle than it actually is. So even though this is a cartoon, it illustrates the same problem we will face when applying these ideas in unconventional reservoirs. Here's the problem in unconventionals. We typically have insufficient logs for the amount of minerals present in the rock. How do we know that? Well, here is a common composition of an unconventional rock from X-ray diffraction measurements. The length of the bars here indicate the relative amounts of the individual mineral. In this sample, we have a substantial amount of dolomite, followed by some clastics, 7 types of clay, and pyrite. So our original composition consists of 12 minerals plus 2 fluids, but we typically have only 4 or 5 well logs to solve for them, which is not enough. So in order to solve for the composition, we are forced to mix minerals that have something in common and give a name to the new class. In this example, this is how the original minerals can be premixed to solve this problem. The first mineral that is a class on its own is dolomite. Then we group the clastics into a single mineral called quartz. But we have to remember that this new quartz will have different properties compared to the pure mineral, and properties from tables may not be adequate anymore. Then we group the 7 types of clay under the name clay. And finally, since pyrite is so heavy, we leave it separate. So after going through this process of lumping minerals into larger groups, we transform the original problem into a premixed problem that consists of 4 minerals and 2 fluids, a problem that we should be able to solve with the amount of logs available. Here are the results we typically get from multimineral analysis. For a given set of input logs, 5 in this case, we select the constituents we want to model and assume their physical properties. In this example, we have 6 minerals: calcite, kerogen, shell, a premix matrix, dolomite, and quartz, and 2 fluids, oil and water. Then we solve for the relative amounts. These amounts are indicated here by the area of the different colors. The other output are the model curves, here in blue, that we compare with the measured curves in red to check whether the results are plausible. Something important to notice in this example is that since we didn't have enough logs, we created a mixed mineral called matrix from carbonates and quartz in the interval of interest to be able to solve for the kerogen properties. To understand the limitations of the standard approach, we should take a look at the assumptions behind it. First, we assume that the log response and the properties are linearly related. So we have to make sure that we use logs that meet these requirements. The second assumption is that we know what the rock is made of. For this, we need prior data, as we showed earlier. So prior information becomes crucial to decide the right mix of minerals. Finally, we also assume that the properties of these constituents are known. And here's the tricky part, because remember that if we have more constituents than logs, we need to group them into composite minerals whose properties are effectively unknown. In practice, the way we solve for these unknown properties is manually by trial and error, one at a time, and this process is also very time-consuming. So if the assumptions are not met, we can not only end up with wrong answers, but it can be extremely time-consuming to get them right, in particular when the lithologies are complex. If we overcome the limitations that make of multimineral analysis a time-consuming application, we could apply it to large data sets to better understand the relations between local and regional geologic trends. Let me show you an example. Here's a map of well locations from a basin scale database of 3,600 wells in an unconventional play, where we analyzed all wells for mineral composition. We will take a close look at the results along the 70 miles cross-section. Here is the mineralogy along the red cross-section. Each track in this figure represents a solid part of the rock, which consists of dolomite, quartz, and calcite. Although calcite is a dominant lithology, we can see regional variations in quartz and dolomite content across the region, with more quartz and calcite towards the center-south part of the basin. So, the benefit of this kind of result is that it helps improve our regional geologic understanding. Let's see now what changes we need to make to understand that approach to get faster solutions. If we have to summarize the workflow of the standard multimineral inversion, we would say that it's mostly a manual approach that requires significant intervention from the petrophysicist. Here is how it works. In the following steps, whenever you see a dashed line, it means that the step was completed by the petrophysicist. And whenever you see a solid line, it means that the step was completed by the computer. So here are the steps. First, the petrophysicist defines a matrix of mineral coefficients from tabulated values. Then, the computer generates synthetic well logs by using the inverted fractions of minerals at every depth. The next step is the visual inspection of the quality of the solution on the screen by comparing with the measured logs. This is the most time-consuming part. If there are mismatches here, the matrix is manually adjusted, and the process is repeated several times. The difficulty is that achieving a good match for all logs using this trial and error process is not only time-consuming but also cumbersome and subjective. In our experience, creating a model for one well starting from scratch can take a few days. Here is our approach for multimineral inversion using a genetic algorithm. Unlike the standard approach, this process is mostly automatic. So here is how it works. After the petrophysicist specifies the range of variability for each constant, the computer generates multiple coefficient matrices. Then, the computer generates the corresponding synthetic logs that are used to compute a numeric mismatch between synthetic and measured logs. Remember that under standard approach, this step consists of visual inspection of the curves on the computer screen. Finally, unlike the standard approach where the matrix is modified by trial and error, here all matrices are modified adaptively using the numeric errors and the rules of the genetic algorithm. Then the process is repeated automatically for a given number of iterations. In our experience, creating a model for one well starting from scratch can take a few hours, about an order of magnitude faster than using the standard approach. Here I'm going to show you a short video to give you an idea of how the iterative process works. What you see here is the matrix of coefficients for a given set of logs in the rows and constituents in the columns. The horizontal axis in each box is the iteration number, and the vertical axis is the value of the constant. If we pick a row in the matrix, for instance gamma ray, the red line in the different columns indicates the values of gamma ray tested for kerogen, shell, and matrix. The green line in each coefficient is the initial value. As you can see, we don't change the gamma ray values for oil and water. So let's start the video. The genetic algorithm generates this red random trial solution for each coefficient and then modify these values depending on the error and the genetic rules until it finds the best solution it can for a given number of iterations. As I said before, one of the main benefits of the genetic algorithm inversion is the increased speed with respect to the standard approach. And it's because of this that we can have new insights into a variety of problems that are much more difficult to solve with the standard approach. So far, we have applied our approach to a variety of problems such as regional mapping of mineralogy from large amounts of wells. We already saw an example of this, and we'll see another one in a minute. Also, since one of the products of the optimization is an updated matrix of mineral constants per well, we can, after proper calibration and quality control, map mineral properties with increased accuracy. We'll also see examples of this shortly. For instance, we have mapped changes in water resistivity, kerogen grain density, and clay composition. And more recently, we've been using also rock physics bounds on elastic logs to constrain the multimineral inversion. So let's see a few more applications. Here is another example of the use of our multimineral analysis to map rock composition and fluid changes at regional scale. First, a lithology map. The pie diagrams in this map show the average rock composition within the interval of interest for each of the 50 wells we analyzed. The rocks we're modeling are clastic in yellow, shale in gray, carbonate in blue, and pyrite in red. This map shows that the northern part is predominantly clastic, that is more yellow in the pie diagrams, whereas the southern part is predominantly carbonate, more blue in this case. Now, this map on the right shows the relative amounts of fluids in the same area after analyzing about 100 wells. Here, the pie diagrams consist of only two colors, red for hydrocarbon and blue for water. We can see that in this case, the amount of hydrocarbon increases towards the south as well. These results are important because lithology and fluid variability are critical for further exploratory and development decisions. And here's the final example. What I'm going to show you now is how we map not only the rock composition, but also the mineral constants that result from multimineral inversion, and relate them to other important parameters such as Vitrinite reflectance in the Marcellus Formation. Here is a map of the northeastern United States, and we're going to focus our attention on the portion of the Marcellus located on the border between New York and Pennsylvania. We're going to examine the result of the analysis in 7 wells that have a complete set of logs, although we're showing only 5 wells here, from well A to the north to well E to the south. Here are these wells in cross-section. The details of the logs in the individual tracks are irrelevant for now, but what I want you to see here is the significant change in depth of 2,000 meters in the interval of interest. The other important piece of information available in this study is measurements of Vitrinite reflectance R0 in the interval of interest, which increases from 1.2 in the shallowest well to 3 in the deepest well. Remember that Vitrinite reflectance is related to kerogen maturity and productivity in unconventional reservoirs. So this increase in R0 indicates an increase in hydrocarbon maturity with depth. Our goal is to see whether we can use the kerogen grain density at each well as a proxy for Vitrinite reflectance in the area. Here is the result of the multimineral analysis in the shallowest well. Remember that our approach has three outputs: the mineral fractions, the model logs, and the estimated mineral constants, and we'll discuss this a bit more in a minute. In this example, we have 6 input logs: conductivity, gamma ray, neutron, density, photoelectric effect, and sonic. And we use them to model 7 constituents, which are kerogen, shale, calcite, quartz, pyrite, gas, and water. So here is the first output, which is the fractions of these constituents versus depth. The second output are the model logs, here shown in blue, that in this case reproduce the measured red logs almost perfectly. We also calibrated these results with volume of kerogen from core data, so we ended up with a plausible kerogen model, this black curve, which is consistent with all available data. But remember that we have a third output, which is the metrics of mineral constants at each well. So what we did here was that we ran the optimization for each well separately, using exactly the same starting metrics, and examined the matrices that resulted from the optimization. Matrices of mineral properties have many coefficients, but I'm going to examine only 2 of them here and see what kind of new insights they can provide. Here is the first one, water resistivity. This plot shows the variation of water resistivity in the horizontal axis versus depth in the vertical axis. Each point indicates the estimated water resistivity at the interval of interest in all wells from A to E. As you can see, there is a decrease in water resistivity around 1250 meters, indicating fresh water in deeper intervals. And remember that water resistivity is a critical parameter in the estimation of water saturation. The second property we analyzed was the kerogen grain density for each well, indicated here in the horizontal axis versus measured thermal maturity, R0, in the vertical axis. As you can see, there is a clear correlation between R0 and kerogen grain density. We suggest that after proper calibration, model kerogen grain density can be used as a proxy to map thermal maturity in the area and help estimate windows of oil, dry gas, or over-matured hydrocarbons. Okay, now let's wrap up with a summary of what we have presented. The main advantage of the genetic algorithm-based multimineral analysis is that it accelerates the connection from log data to results. This is the most important takeaway of this presentation. This means, for instance, reducing the time it takes to create a model from scratch from a few days to a few hours. And having a fast approach allows the petrophysicist to ask new questions that are extremely time-consuming or impossible to address with the standard approach, such as processing large data sets for rock composition, and we saw a couple of examples of this, estimating mineral constants in areas of complex lithologies, and mapping mineral properties such as water resistivity or kerogen maturity. And we also saw examples of this. Also, the models created by this approach can explain the input log data very closely, meaning that the results are plausible. And finally, we have to keep in mind that this approach is not a substitute for the judgment and experience of the petrophysicist. And even though it is significantly automated, it still requires independent calibration data to increase confidence in the results. And before I finish, I would like to thank Dr. Ken Mayer for useful discussions regarding this presentation. That's all I have to say. Thank you very much for your attention.